Okay friends, so right now we will study about solid state. Okay, when we will cover all the aspects of solid state, right? We'll also see some numericals from solid state. Great. So now let us move on in our mission. So first of all, we should know that there are 7 crystals and there are 14 brevis lattice, right? Okay, what are the 7 crystals then? And how do we differentiate them? We'll look at it first, right? And I'll also tell you some tricks how to remember these 7 crystals. So 7 crystals are cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. These are the 7 crystals. And how are they differentiated? Via edge length and via interfacial angle. So the trick is, for the first 3, that is cubic, tetragonal, and orthorhombic, okay, this is how we put. First is obviously A is equal to B is equal to C, like the 3 sides A, B, and C, right? For this, and its interfacial angle is alpha is equals to beta is equal to gamma is equal to 90 degrees. So alpha, beta, gamma are the 3 interfacial angles, right? So at this point of time, the second one will be A is equals to B not equal to C. Third one will be A not equal to B not equal to C. So you see how the relation is, like the equality decreases by 1, equality decreases by 2. Again, the rhombohedral one will be A is equal to B equal to C. For starting from new again, then it again will get like equality gets destroyed by 1, equality gets destroyed by 2, and the last one, it won't be equal. So this is actually pretty much expected, right? Why it is expected? Because as you go down, the complexity of the system increases and the symmetry decreases. For the first 3 cases, the interfacial angle is the same. Alpha beta equals to gamma equal to 90 degree. Even for this also, alpha is equal to beta equal to gamma equal to 90 degree, right? Now, the fourth one cannot have alpha equal to beta equal to gamma equal to 90 degree. Otherwise, the fourth and the first, there will be no difference. So what is the difference in the fourth one? Is that alpha is equals to beta is equals to gamma, but this is not equals to 90 degree. Okay, I'm doing a mistake over here. I'm writing gamma instead of alpha. This will be alpha, 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 not equal to 90 degree, right? And now this fifth one will be that alpha is equals to beta equals to 90 degree, but gamma is equals to 120 degree. The sixth one will be alpha equal to gamma equal to 90 degree, but beta is equals to not equal to 90 degree. Okay, so you see the relation how like alpha equal to 90 degree and gamma is 120. And over here what we see is that alpha is equal to gamma is equal to 90 degrees. So alpha and gamma, so these two are like interchanged. So because over here beta was 90 and gamma was not 90. And over here gamma is 90, beta is not 90. And in the last one, like nothing is 90 degrees. Okay, it's equals to gamma not equal to 90 degree. Okay, so it's pretty easy to remember this, like edge length values and interfacial angles. Like you keep destroying the equality by 1 and again the new one forms and again destroyed by 1 and the last one is not at all. And even for the interfacial angle, the first 3 have the same values. The fourth one, the gamma part is 90 degree, and for the fifth one you can just remember this, like alpha and beta are same 90 degree but gamma is 120, and for the sixth one, like alpha and gamma are same 90 degrees but beta is not 90 degrees, and last one nothing is equal. So these two are actually easy to remember. What is not easy to remember is this. Like how will you remember this order, right? So the trick to remember this order is, there's a saying in Hindi, and if you are not a Hindi speaker, then you should know or maybe make some mnemonics in English for yourself. It's pretty easy if you want to make, right? Just like think about it for 5 minutes and make it. But if you're a Hindi speaker, the mnemonic is this, that सीटी अगर और मारी तो हेक्सागोनल शेप में पहले मोनोक्लिनिक उसके बाद ट्राइक्लिनिक में भेज दूंगा. तो इट्स लाइक सीटी अगर और मारी तो पहले तो हेक्सागोनल शेप में पहले मोनोक्लिनिक एंड उसके बाद ट्राइक्लिनिक में भेज दूंगा. Okay, so CT like C and T. C is like cubic, T is tetragonal, Agad or Mari. So like or is like orthorhombic and rhombohedral, OR. So hexagonal is hexagonal, monoclinic is monoclinic, triclinic is triclinic. So that's how I remember. It's a sentence. If you remember the sentence, you remember the whole sequence. Okay. Advantages to Hindi speakers, not for the English speakers. Now we'll learn about the 14 Brevis lattices. So for the 14 Brevis lattice, we need to consider our previous. Okay, just one second, I have to copy this part. We have to consider SCC, BCC, FCC and our ECC, like end-centered cubic. Okay, and we also need our 7 crystal systems, which are these. Great. So this is cubic. We need our SCC, which is simple centered cubic. We need BCC, which is body centered cubic. We need FCC, which is face centered cubic. We need ECC, which is end centered cubic. So for SCC, all these 7 crystal systems are present, right? And you remember the number 3, 2, 4. Okay, so for this cubic, just put 3 ticks. For the tetragonal one, put 2 ticks. For this orthorhombic one, 4 ticks. And for the second last one, that is monoclinic, just put a tick on that ECC, right? So how many ticks you see? I see 7 for SCC, 8, 9, 10, 11, 12, 13 and 14. So there are 14. So that's a remember. So just remember this number 3 to 4 and remember the fact that SCC is present, like all the 7 crystal systems have SCC. And just put 3 ticks in the front, 2 ticks and then 4 ticks. And for this monoclinic has ECC. So now let us know, if you don't know, about what is all this SCC, BCC, FCC and the related things. Okay, and then we'll also get to know about voids and related stuff to all that, right? So let us start off with our SCC, right, which is our simple centered cubic, as we call it. So SCC has your all the atoms in the corners, right? It has all the atoms on the corners. So let me just draw the things out. Great. SCC. So suppose for like cubic system like this, it will have all the atoms on the corners, just like this. So how many corners are there? I can see 8, right? And each of this atom has a 1 by 8th contribution to it. So what is the total contribution? So 1 by 8 into 8, which is equals to 1. So total number of atoms is 1. right? And now for a BCC, which is a body-centered cubic, it has this like 8 uh, atoms in the corners, and it has also has one atom right in its middle, like in the body part. So the contribution is 1 by 8 into 8 plus 1 for the, which is one of the center one. So the total number of atoms is 2, right? Now for the FCC one, you have like 8 atoms, just like that one. But apart from that, you also have like, so I'm not drawing the 8 ones on the edges. Apart from that, you also have your 6 atoms on the faces. Like there's a like top face, this is the bottom face, this is the side face, and there are like 2 more side faces over here. Like, so there are like 6 side faces. So it already has this 8 atoms on the corners, which has 1 by 8 contribution, giving you 1. And yeah, 6 atoms on the faces. So, and each has half contribution. Total is 4 atoms for FCC. Right. Now we will see some things related to packing fraction. So just know for these facts that 1 atom for SCC, 2 atoms for BCC, and your 4 atoms for FCC. And just for your information, uh, I don't want to go into complexities, but your HCB, which is hexagonal closed packing, this has total 6 atoms. And your diamond crystal has total 8 atoms. Right. And now we will see how actually they are packed and what is the packing fraction of all of them. So I'll just copy. Okay. Okay, just undo. Hmm. Okay, this part is just getting messed up, so I'll just try to leave this part out. Okay, sorry for the inconvenience. Okay, so I'll just uh, again draw it only, or I'll just use this diagram only to tell you. Yeah, so what I'll do is I'll rub this part out. I don't know why it's not getting rubbed out. Now I believe. Oh, finally. Great. Okay, great. So we'll look into the things of packing fraction. Right. And for the SCC one, what you have is like over here you have 8 atoms on the corners, and so what actually happens is that the two spheres that are sitting in the corners of the cube touch each other. So there are two spheres like sitting at the corner. Suppose these two spheres, I'm pointing it out, they are actually big in size, right? So they actually touch each other in the sense that this, suppose this is like this is like this, so they touch each other. So this edge length is A, and it is equals to your 2r, because this size of this is r, right? Because it's like whole atom is like this, something like this, and the sphere form like this. Okay, so the radius is r, so A is equals to 2r we get from this, where A is the your edge length and r is the like radius of the sphere. So the volume of the atom is, volume of atom is equals to 4 by 3 pi r cube, and your volume of your cell is, volume of atom is this is volume of the sphere, right? And the volume of the cell, unit cell, that is a like lattice, which I like this, like the cubic form I draw is a cube, right? Because that's the volume of a like cubic form is given in this, in that sense. And if I write a in terms of r, so we get 2r whole cube, so it actually 8r cube. So if we are called to like find the packing fraction for this, so this will be equals to your 4 by 3 pi r cube divided by 8r cube. This is by the atoms, and this is the whole volume of the cell. Does this make sense, right? Like the, what is packing fraction? Packing fraction is the amount which is packed by the like atoms within the lattice, right? So this is the like volume taken by the spheres, like the atoms, and this is the total volume of the lattice. So this makes sense. So if you do this, you will get like 4 by 3 pi divided by 8, which will give you a numerical value. The value of that numerical value is your 0.524, or you can say the packing fraction percentage is 52.4%. So 52.4% is occupied. This is the occupied space, and the unoccupied space obviously will be 100 minus 52.4, right? Similarly, for BCC, okay, what we will use, I'll just, very sorry for these lines, I'll just try to rub it off. Great. Great. Okay, so this part also got rubbed off, but I hope you got to know the thing that I was trying to say. So for BCC, what you will have is, so if you have this one in the center of the body, and this whole diagonal, okay, this whole diagonal that you see, like from one end to end, and this actually, like what actually happens is, there's like one whole sphere in the middle, and there's like one half of this, and there's one half of this. So this is actually, if you actually draw it like this, what will happen is, it's like one half, and there's the whole part, and there's another half, and so these are like halves. Okay, so like you can say the half of this and the half of this, so it's like r, this is 2r, and this is again r, so you have 4r, right? 4r is equals to root 3a. What is root 3? Root 3 is the body diagonal, this whole line, the value of that is root 3a. If it was a face diagonal, like in the face center cubic, it would be root 2a. Like, you know, a diagonal is actually root 2a. But this is body diagonal, this is not a face diagonal, right? We are not seeing for the face, only one face. We are seeing from one edge to the opposite end, right? So that is root 3a. So over here, what we have is your root 3a is equals to 4r. Did you understand the 4r part? I can tell you. So you have like one atom in the edge, another atom in the opposite end, right? So they actually contribute just half part of their spheres, right? Like they contribute 1 by 8th, but actually when you're looking at the radius, they contribute half of the radius in this whole diagonal, and this opposite one contributes half the radius, and the center one contributes the whole atom, like one whole part of it, so it contributes like 2r of it. So that's why if you add, it's like 4r, and the body diagonal is root 3a, right? So this is the relation between a and r. And similarly, you will just put, like, instead of 2r cube, like a cube is 2r whole cube, in for like SCC, this will be your 4r divided by root 3 whole cube, right, for the denominator, and the this thing will be same. So what you will get is packing fraction. If we say for this, you will get your 4 by 3 pi r cube divided by 4 by root 3 r whole cube. So this is the thing, and you will come to as packing fraction percentage will come to as 68%. This will come to as 0.68. The percentage will be 68% will be occupied. Similarly, I'll just rub this part out so that I can do it over here only. That for the FCC1, okay, for the FCC1, what will happen is, your, this will be a body diagonal now. Okay, like there are like atoms on the faces, so this will be a body diagonal for this time. Okay, And so what do we have on the face? Like there is one in the corner, one in the corner, and one in the face. So again, you will actually have like this will be contributing like 2R. This will contribute half like only R. This will contribute only R. So again, you will have like 4R. But the difference is that this is the face diagonal, so it will contribute root 2A. So again, the relation is root 2A is equals to 4R. Therefore, packing fraction will be 4 by 3 pi R cube divided by your root, yeah, divided by 4 by root 2 r whole cube, and this will be equals to your 74 percentage equal to 0.74. 74 percentage of it will be occupied and the rest part will be unoccupied. Okay, so I hope you're getting some idea through this. So that was the packing fraction, which is very important, right? And now we will look into density of the crystal, which is another very important topic from this. Okay, we'll look into density of crystal. So the density of the crystal, which is you can say as rho, this rho is given as z into m by a cube into n. So what are the factors over it? Z is, as you know, your Z is the number of atoms present per units. It's the number of atoms. For hydrogen, it will be 1. For lithium, it will be 2. For lithium, it will be 3. Helium, it will be 2. Right? Yeah. M is the atomic mass of the element. A cube is the volume. Right? And N is the Avogadro number. Volume, Avogadro number. M is the mass. And we will use this formula in our calculations. Right? So let us take an example. This is a good example. Question is this. There's a BCC structure. Okay, its cell edge is equals to 250 picometer. Now you're told like calculate atomic mass and density is given as 8 gram centimeter. So one thing you need to like be careful over here is your, as you have already understood, the units. So BCC, first of all, this will give 4 atoms, right? So Z is equals to 4. Done. Cell is 250 picometers. This is in centimeters, this is in picometer. We have to convert picometer to centimeter, right? So we can select 250 picometer. So what is picometer? Like 1 picometer is equals to 10 to the power minus 12 meter, right? So 250 picometer in centimeters, what it will be? 250 into 10 to the power minus 10 centimeters. Done. We have density. Just apply the formula now. Z into m by a cube into n. When you're doing a numerical, always write the units beside it. You will never then make silly mistakes. M is what? Your mass. Mass, you have to find it out. Okay. What is a cube given? Cell edge is cell edge is this. So this will be a cube minus 10 whole cube. This will be in centimeter cube. N is Avogadro number. Avogadro number is your 6. You can say like in what I'll say it in a rough term, 6 into 10 to the power 3, right? And 23, 623, and your density that is given as, what is density? Now this is equals to 8 gram per centimeter cube. So you can see the centimeter cube and the centimeter cube will get cut and get mass, which is in gram. So the units are right, so we are in the right direction. And if you just calculate using calculator over here, you will get mass as 37.6 gram per mole, right? So that was it. And now we'll come to your thing of your concept of voids. Okay, and now this concept of voids is a bit advanced and sometimes it's not asked, but I'll just give you some hints of it so that at least you can maybe attempt it while if something like that comes. Right, great. So what are these voids? So what is a void first of all? As in the name suggests itself, that void is like, in spite of the like efficient packing that goes on, like with the spheres in the atom, there are still like voids that remain, right? Like there are still spaces that are like unoccupied, and these spaces are themselves called voids. So I'll just and apart from voids, there is also, as I told you, hexagonal close packing HCP, and this occurs in the form of AB, AB, AB. So this is a pattern in how it occurs. And you also have the cubic close packing CCP, and this occurs in the form of ABC, ABC, ABC. So sometimes once it was asked in an exam that something occurs in this fashion, in this pattern. So what is the crystal system? Right? Something occurs in this crystal like pattern. What is the crystal system? Okay, and okay, great. And I'll also tell you about coordination number because it might be just helpful for you. So suppose we have HCP, your CCP, FCC or FCC, okay, or BCC. So we have just grouped this because these are for the same category, right? So coordination number for these two are like 12. For BCC it's 6, or it's 8, sorry. Okay, coordination number is a number of like atoms surrounding one. Okay, and for SCC the coordination number is 6. Okay, so these are actually important from an exam point of view, so I'm just giving you the idea so that if something comes out of, you will be like won't be shocked or something. Okay, so now let us go into the concept of voids. So we will learn about two types of voids, that are tetrahedral voids and your, you have guessed it already, octahedral voids, right? So a tetrahedral void can be defined like it is a vacant space. Okay, it's a vacant space obviously which is surrounded by four nearest neighbors, right? An octahedral void is something, it's a vacant space which is surrounded by six nearest neighbors. Okay, so that being said, I'll just give you some important relations for both of them. So the radius of a tetrahedral void, like suppose its radius of a tetrahedral void r is equals to 0.225 r capital. So what is r? So r is the radius of the void and capital R is the radius of the constituent particles, radius of particle. Similarly, for octahedral void r is equals to 0.414 r, where r is the radius of the void and capital R is the radius of the particle. Okay, and okay, great. So that was it about voids. Okay, so just remember these two relations. Okay, like normally questions come from here. Now I'll just tell you some, give you some more info so that you can be like expert in this field. So do you guys have heard about Miller indices? What is a Miller index and what is not a Miller index? Okay, so I'll just come to that. But before that, about your SCC, BCC, FCC, I'll just give you some famous crystal structures which fall under all these categories. So suppose it's given NaCl and you're told like what is the crystal system. NaCl belongs to FCC and the coordination ratio is 6:6. Similarly, your CSCl belongs to BCC and your coordination ratio is 8:8. Your ZNS, which is zinc blende, has a coordination ratio of 4:4. And CF2 has a coordination ratio of 8:4. Okay, so these are actually advanced things. I'm just giving an idea of it. If you don't want to remember, it's fine. And okay, then let us go to the next important topic, which is our radius ratio. Radius ratio is given by r plus by r minus. What is r plus? Radius of cation. R minus is radius of anion. And I will tell you like how to remember all these things very easily. Okay, so there's a big chart which you should remember because radius ratio is a very common asked question. So let us take some examples. So if the radius ratio over here is between, there are like some areas for this. So it can be like 0 from to 0.155, from 0.155 to 0.225, from 0.225 to 0.414, 0.414 to 0.732, from 0.732 to 1, and finally 1. So how to remember this? Okay, first I'll show the whole chart. Coordination number for the corresponding ones. This is like 2, 3, 4, 6, 8 and 12. Last one. Okay, and your the structural arrangement, or you can say like geometry structure. So this is linear, this is trigonal, planar, or triangular. Trigonal, I'll just write it, trigonal, planar. 4 it is tetrahedral as you expected. 6 is octahedral. For 8 it's, you can say it's cubic or you can say it's BCC. For 12 it is CCP or HCC. HCP, that is cubic close packing or hexagonal close packing. And so they may just give you a radius ratio and they might ask for what is the structure of this. So how to remember this? Like okay, so how to remember this is you can see like how I remember this. It's like 15 over here, like 0.155. So it's like 15 over here, and the square of 15 is 225, right? And if you actually just keep on writing this like 0.225 to 0.414 and then 0.414 to 0.732, actually if you keep on writing the numbers you will easily find it out that this will be the case or this will be the scenario. Okay, so that's how I learned it. Actually I just kept on writing this and automatically the numbers got fixed in my mind because there's no other way actually to remember this, otherwise you might lose some marks in exam. Okay, so this is actually easy, right? Like for tetrahedral coordination number will be 4, for octahedral coordination will be 6, for trigonal planar it will be 3, for linear it will be 2, like similar to your VSEPR theory you learned. Okay, I'll just give you some examples as well. For 6, as I said, coordination for 6 Like example will be your NaCl or MgO. For coordination number 4, you can take example as like ZNS or CuCl. For trigonal planar, it can be like B2O3. For cubic, it can be like or BCs, it can be CSCl, NHR, NHB, like NH4Br. Okay, ammonium bromide or CC metals, kind of metals. This is actually very important for NaCl. ZNS is important, and okay, these two are very important. Okay, now I'll just give you a glimpse of what is Miller indices. Miller indices. So this is actually coordinates of an atom, which and we take the reciprocal of the coordinates. So suppose the coordinate for an atom is 1, half, and 2, right? So the Miller indices will be 1, 2, and half, and we have to convert it into whole number. So first, these are coordinates. You take the reciprocal, and then you convert it into whole numbers, right? And you get like you multiply by 2, right? You get a whole number 241. That's it. So I'll just show you some examples. So suppose this is a cube. Okay, great. You have z coordinate on this side, x on this side, y on this side. So what will be the coordinates of this shaded plane? Right. So coordinates of this shaded plane. So what is z? So suppose this is like 1. This is 1. And you can see that this actually just keeps on going, right? Like this is, you can say this is like parallel, this cuts z at 1, but this is parallel to your x and y. So coordinates you can say as infinity, infinity, comma 1. So you have to take the reciprocal of that, so it will be 0, 0, 1. Similarly, what will the coordinates, Miller indices of this? The Miller indices, you can see it cuts y at 1, but it is parallel to z and x, right? So Miller indices will be, so how do you write the coordinates? First, I'll just x, y, and z, right? So 0, 1, 0 will be its coordinates. Similarly, for this plane, it cuts x at 1, but is parallel to z and y. So coordinates, Miller indices will be 1, 0, 0. Some more examples. Okay, so what will be the coordinate of, suppose if I use a different color, we could, what will be the coordinate of this plane? It looks so good, huh? Yeah, thanks. So what are the coordinates of this plane? The coordinates of this plane, so this is like z, this is x, this is y. So what you can see from this plane, that it cuts x at 1, it cuts z at 1, and it is parallel to y. Coordinates will be this, Miller indices will be 1, 0, 1. Understood? Let me take another color and draw it in the same diagram. So what will be the coordinate, or let me just rub this blue. Okay, let me just try to do it over here only. If I connect your, I'm connecting x and y, right? Like this, this. So it's like connecting to x and y. So it cuts x at 1, it cuts y at 1. So coordinates will be 1, 1, and it's parallel to z, infinity. Miller indices will be 1, 1, 0. Great. Let me take just one last example so that you can fix like last two examples. When will it be 111? So try to think when it will be 111. Obviously by now you know that all the three like axis has to be get cut, right? Like this. This will be 111. Now tell me this, that okay. So if you have something like 1 minus 1 1, so if the coordinates are like 1 minus 1 1, then you have to write it as like the Miller indices will be 1 1 bar 1. Okay, and if it's like minus 1 1 1, the Miller indices will be 1 bar 1 1. So actually in the Miller indices you don't include the negative part, you write or give a bar over it. So that's how you do it. And with that we come to the most scoring part. Okay, just before going to the most scoring part of our uh, solid state, I'll just tell you that for like a so Miller indices are actually called like HKL values, right? Given like HKL values. So for which HKL values it will be SCC. It's just for all values of HKL. Okay, the three coordinates of Miller indices like x, y, z coordinates after they are reciprocated and given the whole number, they're called HKL. And for SCC, all the values of HKL are applicable. For BCC, when H plus K plus L is even, it is allowed. When H plus K plus L is odd, it is not allowed, or it cannot be in BCC. It cannot have a BCC structure. And for FCC, H, K, L has to be all odd or all even for it to be an FCC structure. Okay, great. And now we come to the so-called most scoring part of our uh, solid state, which is nothing but, as you have guessed it, is the Bragg's equation. Let me use a different color. You might be getting bored seeing the same color. Bragg's equation. So Bragg actually showed that when light is actually reflecting like this is actually diffraction. Okay, it's not reflection, it's actually diffraction that happens. In many books it's called reflection, and it is used as reflection, many will say, but actually the truth is that it is not reflection but diffraction. So as you know, this angle of incidence, this angle of reflection as I say it. Okay, so and we take, like, you know, by laws of reflection and all those things, this is like theta. So and this portion is d, and you use a particular wavelength. This is actually you use an X-ray, which is a particular wavelength lambda. And Bragg said or gave a relation between that 2d sine theta. So this is actually theta. This is d. This portion. Sorry, I'm so sorry. This portion only, not this portion. So this distance, right? Is a separation between the two. Okay. So he said that 2d sine theta is equals to n lambda, where n is the order of reflection. We 1, 2, 3 as given in the question paper. And what's the relation between d and your h scale coordinates is that 1 by d square is equals to h squared by a squared plus k squared by b squared plus l squared by c squared. And a, b, c are the quarter lengths of the lattice, or the edge length you can say, and h scale are the like the Miller indices. Okay, so D can be for a cubic lattice where A is equal to B is equal to C. It can be said A is equals to A, D is equals to A, by h square plus k square plus l square. But normally you can use this also for when it's not a cubic lattice. 1 by d square is equals to h square by k square plus a square by e square plus k square plus by b square plus l square by c square. Okay, so these were some equations, and now let us look in the final aspect, which is what is the angle between the two planes. So suppose you have two planes, right? h1 k1 l1 and h2 k2 and n2, and you have to find the angle between two planes. So it's given by cos theta equals to h1 h2 plus k1 k2 plus l1 l2 divided by root of h1 squared plus k1 squared plus l1 squared, and again root of h2 squared plus k2 squared plus l2 squared. Okay, so that is how you find the mm, angle between the two planes. And that was more or less of it. And I'll just tell you, maybe if you've forgotten, some basics of semiconductors, because semiconductors, why I think semiconductors are important, though it's very theoretical. Semiconductors are used everywhere, from your phone, laptop, and in this digital age. So, question. So, semiconductors can easily come. Okay, so semiconductors, what you need to know is like it is between metal and non-insulators. So, like two bands are there. One is your conduction band, and one is the valence band. Okay, and there's a small gap between them in semiconductors. And semiconductors can have three types. One can be a intrinsic semiconductor, which is on its own, like from beginning, or one which is doped, which can fall under N category and P category. These are doped, right? So your N category semiconductors actually uses the concept of like uses your group 15 elements, which has like extra electrons. Group 15 as in, you can say, your SB, AS, plus your group 14, that is silicon. And this is a group 13 elements, which is deficient of electrons. So it uses concept of holes, and this uses concept of electrons. So this uses like concept of holes, like silicon plus your group 13 elements, you can say gallium. So this works on the concept of donors, which donates because it has extra electron. This works on the concept of acceptors because it has lacking electrons, right? So in N type, you have conduction band, you have valence band, and this is N type N, and you have this over here. You have the donor level, right? This is donor level, and in P type, you also have the conduction band and the valence band, and over here you have the acceptor level. So this level is also called Fermi level. Okay, yeah, that's more or less of it from your solid state. If you know this, you should be able to answer. I'll obviously do some numericals as well, but actually this video has been very long, and so just go through the concepts in the next video only, which I'll be uploading in some time. I'll show you some maybe easy concepts and easy numerical solutions. Okay, and apart from this, is the Schottky effect and Frenkel defects. You can learn it from anywhere. It's like class 12 stuff, so that's not tough. That doesn't really come as well that much. So I hope you enjoyed this video. There were some, like not so much organized maybe, and some lines over here and there which I had cut. But because it's a small channel, do forgive and show some support and practice, and you'll do very well. God bless and have a great day ahead.